Hey everybody, it is Miss List and I am here with 5.3 from AP Chem, and this has the section titled Rate Laws and Graphing. So in 5.2 we learned about the generic rate equation. That rate is going to equal K, that's our rate law constant, times the concentration of each of the reactants. We always write rate laws with respect to the reactants disappearing. And if I had 3 reactants, I would keep going. And the exponents tell us the order of the reaction. And that tells us what effect does changing that concentration have on the rate of the reaction. Well, it should be no surprise that when we have equations, scientists love to graph. And so that's where 5.3 comes in, is we're looking at the different types of graphing that we can do with these rate laws. Now, this gets into some math that is in the calculus realm. So we aren't going to be talking so much about the calculus or the math that goes behind it. We're going to be focusing on the result of the math. So we have 2 different but related perspectives. On the left, we have what's called the differentiated rate law. This expresses how the rate depends on the concentration of reactants. Multiple trials are needed in order to determine the order. And this is what we were doing in our last section when we were looking at the method of initial rates. And it helps us describe what's happening. If I double A, does the rate also double? Then that would be first order, so on and so forth. The hindrance is that we have to do multiple trials. That's the frustrating part. The positive is that it allows us to describe what's happening at a molecular level, because I can see which substance is causing what to the rate. And so multiple trials are needed, so this can be a tedious process, but it helps me determine the overall mechanism, and that's what we call reaction pathway, and determine what substance is causing the rate to increase or decrease. And so there's both pros and cons to the differentiated rate law. Then on the other side of the coin, we have what's called the integrated rate law. And in the integrated rate law, we would be looking at how the reactant's concentration depends on time. So it's just looking at it a different way. When we did the differentiated, we're doing how the rate depends on the concentration of reactants. Well, here on the right-hand side, on the integrated rate law, we're looking at concentration versus time. The pro for the integrated rate law is that only 1 trial is needed. So I only have to do 1 experiment. And what that allows me to do with that 1 experiment is to determine the overall order. And so I can use this then to determine, once I understand what the rate law is, I can use it to determine any reactant or product present at any time during the reaction. So again, the pros would be 1 trial, and I can zoom in and look at how any reactant is in product, how much is present at any point in the reaction. And this is also how we can determine the half-life of reactions in nuclear decay processes. So lots of pros here on the integrated rate law side. When we compare what the graphs look like with the concentration versus time with the differentiated rate law, that's what we're looking at here in this section. And the thing I want you to notice is with the integrated rate law, we only have 1 that is linear. So when I look at concentration versus time, the only one that would give me a linear plot would be if it was 0 order. And then these are the equations that go along with each of these graphs. So linear makes analysis a lot easier. And so this is a drawback if I have something that is first order or second order. Those are not linear plots. I can see that I've got more of a curve, and then this has a square in it. So these are not linear functions when we talk about it in a math sense. However, when I take and look at the integrated rate law, and when we say integrated, we're talking about integrals. So again, calculus involved. And since many students that are in AP Chem have not had calculus, we're not going to simply jump into the math. You can look at the derivation if you're into math of how we get from the differentiated to the integrated. But for us, what we need to know is that when we use the integrated rate law, look at all the lines are linear. That makes it really easy for us to determine the order of the reaction. The slope of each of these lines is going to be equal to k. So this is also a way that we can figure out our rate law constant because the slope is going to equal the rate law constant. The other thing that I want to point out is some of these do have a negative slope. So if this was 0 order, this was first, and this was second, we just need to remember that if our slope is negative, then k should always be a positive value. So if our slope is negative, we would change that to be a positive. So how do we use the integrated rate law? Well, in lab, a chemist will measure the rate of a reaction, and usually we just do we would do one reaction, not varying the concentration, but just one reaction. And then we'll take that data and we'll prepare 3 graphs. The 3 graphs that we will compare is the concentration versus time. We will graph the natural log of the concentration versus time. And we will prepare a graph of 1 over the concentration versus time. And what we will do is we will look and see which one gives me a linear slope. So the one that produces a straight line or has a linear graph will tell us the order. So if this A versus time is linear, that tells me it's 0 order. If it's ln versus A versus time, that would be first order, and then 1 over A versus time would be second order. We won't get into the graphs for like 3rd order and 4th order because that isn't really covered in AP Chem. These are the ones that you're expected to know. And so what's nice about this is I just have to do one concentration. I'm not changing the concentration a bunch of times like we were looking at in 5.2. And I just use that data to create 3 different graphs. And if you use a graphing program like Microsoft Excel or Google Sheets or even a graphing calculator, that can make the analysis really fast. Now, we can also use this to answer questions like how long will it take or how much is left after a certain amount of time, because we have a t component in each of our equations. We have time is t, and then k is our rate law constant. And the fun part about these equations is these are actually listed on your equation sheet. So you don't have to have these memorized. What I'm highlighting here in red, those are listed on your reference sheet. And they're in order. So I think they're written in one above another, and they will be in order 0, 1 second. They're not labeled, but they will be in that order on your reference sheet. And so that is super easy to help us remember which equation goes with which order. So take-home points before we look at some example questions. The differentiated rate law. It has advantages. We can see what's going on at a molecular level, but it requires multiple trials. The integrated rate law, we do one trial at one concentration, and it allows us to answer questions like how long will it take or how much is left. But the drawback is you're not getting any molecular information about it. We don't know the mechanism of how the reaction happens. A big part of what you'll be asked to do is look at graphs and determine the order from graphs, which is exactly what we're doing here in our first example. It says, what is the order of the reaction with respect to N2O5 if the data from the lab is plotted as shown on the graphs below? Explain your reasoning. So again, we have three different graphs and we want to look at our axes. So this one has the change in concentration versus time. So this would be my 0 order graph. Natural log of concentration versus time is going to be first order, and then 1 over the concentration versus time is going to correspond to second order. And so whichever one of these gives me a linear graph is going to be my order of the reaction. So I would say that this is first order. And the reason I know that is because the ln versus time graph is linear. Similarly, on number 2, we want to look for what is the linear plot. So they are listed in order. They won't always be listed in order, so be careful of that. But this one is concentration versus time, so that would be my 0 order graph. This is ln, so first order, and 1 over is second order. And so they have the dashed line to show you the straight line comparison. So we can definitely see that graph 1 is not linear, graph 2 is not linear, but C is definitely linear. So I would say that this is second order. And my explanation is because the 1 over the concentration versus time graph is the linear plot. On question number 3, we're answering one of the things that we can use the integrated rate law to do, which is how long will it take? So if I come back up here, how long will it take? And it says it's first order. So I can use the first order rate law to determine how long it will take. And so I'm going to erase a little bit just because I got a little crazy when I was labeling. But it tells me it's first order. So this is the equation that I want to use when I'm solving this problem, because I have a rate law constant that they give me in the problem, and I can then use this information to solve what they're asking me. So I'm just going to rewrite the equation here. So in this problem, they're saying that they give us the rate constant, and it is equal to 9.2. So that's going to go in for K. And they want me to find T. T is my unknown. Now, one thing that I do want to point out is what each of these values mean. And ln of A is the amount left. And this ln of A naught would be my starting amount. Now, they did not give me actual values of molarity or anything like that. They gave me percents. So if 80% decayed, that means that 20% would be left. And so I'm actually going to use the decimal form for my value, which would be 0.2. So I'm going to set up this equation as ln of 0.2 equals ln of 1, because 100% would be 1. That's how much I started with. I'm looking for T if the value for K is 9.2 times 10 to the negative third. So I would simplify this equation and I would solve it for T. If you do that, and I'm not working through all the math right now, but you should get a T equals 174.9 seconds. So this is an answer of how long would it take. And so that is one way to use the equations, not just understanding which equation matches up with which graph like we did for 1 and 2, but you can actually plug values into the equation and solve. On number 4, we have this reaction as second order, and they give us our K value, so the rate constant K. And they say that the initial concentration is 0.2, and they want to know how much is remaining after 10 minutes. The first order rate law is different than the second order. So we would need to go to our reference sheet and see that the second order is 1 over the concentration minus 1 over A naught equals K times T. And in this problem, they give me a value for both K and T and the initial concentration. So I want to know how much is left. So I'm going to be looking for the A value. If I start with 0.2 and my K value is 5.76 times 10 to the negative second, and my time is 10 minutes. So again, using math and simplifying, trying to isolate A in the bottom. I'm not going to step through every piece of algebra there, but you should get, if you want to practice that, A equals, the concentration of A is going to be 0.179. And that is a molarity because that is what we were looking at, molarity per minute. And so that should be my final answer. Now, the half-life equation can actually be derived from the first order rate law. And so the first order rate law looks like this, and we can rearrange it to solve for t. So I would be dividing by k on both sides. And so I can rewrite it as t equals natural log of a naught over a times 1 over k. Well, if I set the time equal to 1/2, then we can do some more math. And this is the derivation of how this all comes up. Simplify it, and we end up with the half-life equation here in this box. This is also on the equation sheet. And so this is another way that we can figure out K, especially if it is first order. We can use this information. So it says a certain reaction is first order. Determine the amount of time required for the reactant to go from 0.5 to 0.25 if the rate constant is 1200. So this is 1 half-life because it's cutting in half. They give me the rate constant. So if I know that it's first order and I know that it's a half-life, they're calculating 1/2. It's decreasing by 1/2. I can actually use this simplified equation to do that. So I do 0.693 divided by my K value of 1200. And if I do that, then I get we should keep 3 sig figs? No, 4 sig figs. Excuse me. Because this period here wants me to keep 4. I get 5.775 times 10 to the negative 4th, and that would be in seconds. How did I know it was seconds? Because of the value for K is in seconds to the negative 1, so seconds would be my label there. For number 6, the first order decay of iodine 131 exhibits a rate constant of 0.138 days. What is the half-life? So again, this is a half-life. It's asking me for the half-life, the time it takes for 1/2 of the substance to decay. And I'm going to do the same calculation I did before, 0.693 divided by my rate constant in the bottom. And that's going to give me a value of 5.02. And this time my label is in days because that is what my rate constant label was. It was in days to the negative 1. So my answer is going to be in days. Now, I realized that I skated through how this derivation happens. It's not super important to understand how we get from the first order integrated rate law to the half-life equation. This is just for my friends that are super into math and want to understand how we get from this to this guy. Nick talks you through it. The important thing though, the take home, is that we can use first order. Any half-life is always going to be first order, and we can use a simplified version of the first order equation to figure that out. I think that's it for 5.3. Some students tend to get a little hung up on 5.3 because of the equations and the math. I want to focus on what we were talking about at the beginning, that what is the difference between the differentiated versus integrated, why each one is important, and then how we use each one in chemistry is the most important part. All right, that is all I have for 5.3. Thanks for being here.